conditions like hook runs at every clock tick and idle hook runs repetitively as long as the CPU is idle. It also has a mechanism for checking for and preventing stack overflows, and also if you need tracing, you can add additional hooks for tracing. So this is how we configure. Basically, there's a file called FreeRTOS.config.h, and you keep defining symbols to enable preemption or not. You can enable or disable several hooks if you need. Then, well, we have some numerical parameters like how long a task's name can be. Then, if I want to use tracing, if I want to use mutexes, and so on and so on. So this is what a minimal main function looks like in the hardware I use with, mainly Atmel microcontrollers. Sys clock init and board init are completely microcontroller functions. They have nothing to do with FreeRTOS. And the only FreeRTOS related function here is task start scheduler. Until I run the scheduler, there is nothing about FreeRTOS, and once I start the scheduler, it all runs, starts running in FreeRTOS context. Well, a scheduler without any tasks is nothing. So, using this prototype, I can add some tasks. A task is basically a void function, which ideally has an infinite loop inside. And then I register my task by calling the task create function with a pointer to my function, with a string name, a stack size. So stack sizes are fixed. That's how we can check for stack overflows. I can pass a parameter. I can pass a priority, an integer. Then if I need, I can keep a handle to my task if I need to kill the task or play with its priority in the future. Here it's null because most of the time you don't need that. And then we start the scheduler. So I said we have several hooks. These are some example hooks available. They are normally defined as weak symbols, so if you need to use them, you can redefine them, or you can compile them out. Application idle hook, as I said before, runs whenever the processor is idle. A tick hook is at clock tick. A malloc fail is, well, obviously runs whenever a malloc fails. A stack overflow hook runs whenever a stack overflows, and you see I get a handle to task and even the string to the string parameter to the task name, so I can immediately do something about which task has been overflowing its stack. We have a semaphore API. Basically, to create a binary semaphore, you give and take them. Something important about interrupts is that a lot of API functions have their from ISR variant. Like here, I have X semaphore give and X semaphore give from ISR. If I'm running from within an interrupt service routine, I need to use the from ISR routines so that it doesn't mess with context switching. Also, messaging queues have their variants with send receive and from ISR. An important part of the API is delay. Basically, there are two functions. One is simple delay. You call it function and your task gets delayed the number of ticks you pass. And there is a smart function called delay until, where it takes two parameters, previous wait time and some increment. And as I'll show you now, it's smart in a way that it automatically increments its own previous wake up time. And it increments the previous wake up time in a way that the task always calls periodically. I should have called the frequency actually period. So I have a wake up period, I get a last wake time, and then I start an infinite loop where I call task delay until. See that I don't do any manual updating, and then code my whatever task functionality is. And here is a demonstration of how it keeps the tasks periodic. The bottom is the purple line visible?
No.
Slightly. Yeah, I should have picked better colors. The purple task shows that it's a basic LED switching task, so it's active only on the transitions. And if you look at the top green line, it shows a high priority task which takes the CPU and holds the CPU as long as the green line is high. And as long as it's low, the task is idle. So what I want to show here you is whenever the green line is up, the CPU is busy with a high priority task. The switching at the purple function is delayed. It arrives late because it has a lower priority. But even then, even if it misses some deadlines, the next deadline still keeps periodic. So the wake up time updates in a way that's not the actual time it wakes up, but actually when it was supposed to wake up. This way you get some jitter, but overall in a long period, the amount of firings is constant. So, we have several flavors. Let me talk about the license of FreeRTOS. The main FreeRTOS license is so-called modified GPL. They have a modified GPL because all the tasks, all the application-specific code gets statically linked into FreeRTOS. So, according to GPL, everything must be re-released on GPL. So they modify it in a way that you can statically link your application called FreeRTOS